The floor is yours.
Thank you.
Thank you so much. So, hi from my side. Okay, we were already introduced. That was actually my first point. So, I'm an FPGA developer at Thales, Germany. Yeah, I'm here with Nico, being the group leader of Fraunhofer. Our third main contributor, also from Fraunhofer, cannot be here with us today. Tore Gerlach, who's still in between the worlds, having had a talk at the QCE in Canada last week about this very topic. Yeah, so Thales is a big company, a French company with roughly 80,000 employees. I checked, I think last year revenue 18 billion around that. Last year we were trying to find practical applications for speeding up with quantum algorithms. In this regard, we made a competition between the sites with different use cases, and we as Thales Germany, together with Fraunhofer, try to explore how we can speed up the FPGA development process. First of all, I'll give a very quick introduction. What is an FPGA? Has any one of you ever heard of FPGAs? Okay, yeah, quite a few, because I mean they are kind of common in quantum environment as well. Still a little introduction. FPGA is obviously the coolest thing on the slides here, being in the middle between CPUs and ASICs. CPUs and ASICs being like on the extremes. CPU is a very general purpose processor, thus being kind of inefficient and therefore still super low unit cost because they are manufactured in super big quantities. And the ASICs, application specific integrated circuit, on the other hand, is very domain specific for particular use case developed, thus very high development costs and initial costs that are super high. But therefore super efficient, super fast. FPGA is in between. It's kind of a little bit like an ASIC, but reprogrammable, field-programmable gate array. And yeah, as that being still pretty efficient, with comparatively towards an ASIC low development cost. So where FPGA is used, as you probably know, as for research, development, quantum hardware, quantum emulation. For example, our colleagues from Fraunhofer have the Evo Annealer. If you could give us one or two key facts about that.
Yeah, actually, it fits to what we heard before. So before we heard a lot about QUBOs and how to solve these kind of problems. And this Evo Annealer is also some kind of quantum-inspired FPGA design where we can what we developed at our institute, and that you can use to also get approximate solutions to QUBOs, right? So we use it in our experiments, and it's just a pretty nice thing, right?
Okay. So next to that in research, we obviously as Thales use FPGAs in industry applications, telecommunications, automotive and aerospace are some huge domains where FPGAs are used for tasks like waveform generation for radio devices or so, aerospace, radar applications, and yeah, next you can see the detector at CERN here. FPGAs, where FPGAs are used in like hundreds or thousands of those as a first level for data acquisition and data filtering, because you can implement quite some logic and at a very high data throughput in FPGAs. Okay, so and all those industry sectors have one thing in common, where we also use FPGAs as a defense electronics company, which is crypto. And FPGAs are especially useful for that because, well, first of all, high data rate, and you have a very deep control to a low level over the functioning of the crypto algorithms, which is important for us because cryptology is susceptible to things like side channel attacks. You might heard about these, which is where like a given hardware implementation might be attackable because just of certain characteristics of the implementation. For example, if a certain operation like a multiplication or whatever takes this and that specific time or energy, adversaries can observe the system very detailed and make many measurements and can compromise very secret data, which is why we use FPGAs for that, because yeah, in the worst case we could reprogram them in field to get around if we notice an attack. So very quick introduction, how is an FPGA programmed? So you start from programming code. In case of FPGA, this is Verilog or VHDL. You start a tool similar to a compiler for software. This is called a synthesis tool for FPGA development, which translates this HDL code into a netlist, which are basic primitives, Boolean gates like AND OR or so. And this netlist is fed to a place and route tool, which maps those basic elements of to the building blocks of the actual FPGA grid. And the place and route steps is very, very time consuming and does not usually lead to very favorable solution qualities. And that's why we wanted to improve this step. So the placement step, as I said, maps those in graph theory talking the facilities like the logical functions have to be mapped to the physical locations on the FPGA grid. FPGA being a grid of like 1,000 times 1,000, like 1,000,000 locations, each a very small Boolean function in like 4 or 5 variables with one output. And this is obviously a problem that is pretty huge and is NP hard, a quadratic assignment problem, and there's no good approximation algorithms. That's why, yeah, solution qualities are nowadays pretty low. And as an FPGA developer, if you have to wait 5 hours for a solution and then the tool tells you, oh, you failed timing by 1 nanosecond or so, it's not nice. Okay, after placement comes routing. That is just connecting the source and sink pairs with some additional considerations like avoiding congestions, where just like one highway route or whatever is just congested and you have to take big detours. So the general goal is to minimize the longest wire length in order to increase the maximum clock frequency for the FPGA and increase the throughput. Okay, so I talked way too long, and I hope you're still okay. And yeah,
I'm good. Is this a
Nico
clicker thing? Okay. Okay, great. Thanks, Stefan. Yeah, and now the question is how we address this by some quantum method. Okay, so as I said, we already heard about Cubo. So this is also our approach. We first, or in this talk, we are only addressing the placement problem, right? So Stefan introduced both, but we are mostly interested in the placement part here. And yeah, what we did is coming up with a Cubo formulation of this placement problem, of a QOP problem. And so in this original QOP, we have a flow matrix and a distance matrix, right? And what our goal is to find a permutation of these, say pairs of locations and facilities that minimizes this cost function here. So you see that originally this is not a Cubo, right? But of course you can rewrite this in terms of a permutation matrix. So instead of optimizing over this abstract object like a permutation, we are looking at a matrix P here, and okay, you can write it down as there. Maybe I also do the Italian thing as the guy who talks earlier. Why is this not the slides that I see there?
Oh.
It's not that slide, right?
No, I confirm.
Okay, now I also understand like why people are not.
We are currently on page
Next
slide 9. Yeah.
Okay, right. So Yeah, so earlier I was at the slide before. Yeah, okay. Okay, now, okay, let's do it like this, right? Okay, we have a problem formulation like that. We have a permutation matrix, flow matrix, distance matrix, and of course we also have some constraints, like a constraint that says that is important for the permutation matrix, which says, okay, in each row we're gonna have only a single one, and also in each column it says at most one. Okay, so we have some constraints which make sure that our matrix P, which will be our QUBO solution, is actually a proper permutation matrix. And then playing a little bit with this formulation, you eventually come up with this QUBO here, and now Z is a binary vector. It's m times n dimensional, so one is the number of locations and the other one is the number of facilities. And you can basically think about it like we are just writing down these rows or columns, however you like, of the permutation matrix. We write it down in terms of Z, right? We write it down in terms of the vector we are optimizing over. And yeah, what you directly see here, this because it's red, is that this will be a large number eventually, right? So we have a large number of facilities and a large number of locations, plus we have some constraints here, right? And we already heard about this earlier, that QUBO, you know, the U in QUBO means actually unconstrained, right? So it's always a problem when you try to put some constraints into a QUBO. It always comes at it always introduces some hassle, okay? And the problem is how we address it here, right? On the one hand side, we want to address the size, the sheer size of the QUBO, and on the other hand, we want to address the permutations and the constraints. And actually, it turns out that a single method helps us to solve both, and it's called cyclic expansion, or some people also call it alpha expansion. And the idea is, it's pretty neat actually. So it's based on the fact that you can just decompose a permutation matrix as a product over small permutation matrices, right? So you can do this. And so the idea here, the idea of cyclic expansion is instead optimizing directly over, can we go back one slide? Yeah. Instead of optimizing directly over our decision variable Z, you can think about you are only optimizing over some permutation matrix which changes these Z's, right? So that's the general idea of alpha expansion. And here, what you have is you have a product of small permutation matrices, and you're optimizing over these alphas, right? So these alphas, they act as a switch, right? When the switch is 0, it means we have identity matrix here. So it's basically nothing is multiplied by 1, right? And if the alpha is 1, it means we are multiplying this permutation. So by choosing a specific alpha vector, you are choosing a specific subset of these permutation matrices, and you multiply them together, and which gives you the actual final permutation that you will apply, right? And the nice thing is that you can choose which small C's here, which small matrices you're optimizing over, which allows us to have a very natural way to split the large problem into many small sub-problems, right? Because we can, in each iteration, we can present only a small subset of permutation matrices to the algorithm and only choose some of them, right? So it's very different to what you usually do. Usually, you take a large QUBO and split it into pieces, right? But this is not what's happening here. At all the time, you are basically acting on the full QUBO, but you're only limiting the choice of actions that you can do to come from one solution to some other solution, right? So that is nice. It helps us to make a smaller problem. And on the other hand, it also helps us to include the constraints, right? So Stefan already said we have a lot of blocks in the FPGA, but actually they are not all the same. Some are just for memory, some are just for I/O, some are just for something else, right? Some RAM, whatever. And as I said, what people usually tend to do is, yeah, they encode it as some additional term here. It's bad. You have to choose the lambda. You have to come up with a proper realization of constraint. It's not obvious how to do this, so we don't like it in general. right? So the point here is by choosing the specific subset of permutation matrices, here by choosing the subset we are optimizing over, we can effectively control what steps the algorithm is allowed to do, and so we can effectively include constraints into our problem, which we otherwise have to add on top and have to otherwise we have to tweak the objective function, but that's not necessary here, right? So here, I mean, you get the broader picture. What we do is, because we are just permuting an existing solution, we are starting with some random initial solution, and then we have two loops, right? One large outer loop, we run it until convergence, and some smaller loop. And in this smaller loop, we are sample small disjoint 2 cycles, basically swapping the 1 entries in the solution, optimizing over, we update our current solution, and we do this until every 2 cycle we want, right? Every 2 cycle we allow, which realizes our constraints until every of these 2 cycles is visited. And then we have the outer loop, which we run until convergence. So we solve a large series of small qubos, right? And eventually ending up with a permutation matrix that when we multiply it to that solution, we get that solution, right? So we get a new layout and a new placement for our problem, right? For our FPGA design. And we did experiments with synthetic data where we just said, okay, let's think about some easy imaginary synthetic FPGA design and some real-world lattice ECP5 FPGA. And we compared with classical software, but also with D-Wave solver. And we also compared to state-of-the-art placers like simulated annealing and some other weird approach. And okay, yeah, so what the actual outcome is that, of course, depending on the size of the chunks we are splitting our problem. I mean, we heard earlier that 180 would be some proper size for a D-Wave QUBO, but actually, those of you who tried this out know you have to deal a lot with these chains problems. So in reality, you have problems which are much smaller, right? So we are looking at maybe 60, 80, or 100 variables here, and in all of the cases, we see a nice degradation of the QUAP cost, so we are arriving at good solutions. Of course, the larger the problem is, the better is our worst case, right? So this is like the worst case solution, and the worst case gets better and better, and it also works well for a much larger number of facilities, right? And yeah, so here, just to get an idea what it looks like. If this is the initial placement, after a single outer iteration, you have this guy, and after 50 iterations, you are almost there at a design which has a much lower QUAP score than what you get from simulated annealing or from other algorithms which were implemented in this open source toolchain, right? And this is something where I think you will say something more about that open source thing here, this uses. You like to say something about it?
Yeah, well, I mean, this is...
We still have time, actually. Do I still have time?
Yeah, 2 minutes.
Ah, then, okay.
Making sure you all have no time for questions. So yeah, our framework was we tried to use open source tools, which is there with Yosys. This is the Yosys open source synthesis suite, and which is just a synthesis. So this generates the netlist, as you can see here, and then next PNR, which is the place and route tool, open source. And yeah, well, first of all, it's open source, so we could, in theory, modify the C code, but it also exports the design to Python or several APIs. And we accessed that with a Python framework. And yeah, after packing is a step where the basic gates, like the 2 input ANDs, are put together in FPGA architecture specific functions, like usually 4 or 5 input functions. We exported that in our Python framework, did some pre-computation, and then gave that to the Fraunhofer framework with QUBO and handling of the quantum computer, which can be fed back later to before the route algorithm into next PNR and can generate a valid bit stream.
Right, so that is important point. This is why I also like to that you mentioned this, because we actually, so it's not just some experiment in some paper, right? We actually implemented the D-Wave-based QUBO solver into existing open source software for actually FPGA design, right? So you can use it and say, okay, now I want to have a placement which was computed by D-Wave QUBO solver, right? You can do this. Okay, we have other results, but I think we don't have to discuss them. Maybe you ask some questions rather. Okay, I think we are good. Okay, yeah, thank you.